Hello everyone. Previously, we have seen the operation of a PN junction diode, its characteristics, and also some of its parameters, including static and dynamic resistance. And we have also solved some numerical examples of that. Today, we will see the equivalent circuits of diode. So what is an equivalent circuit? An equivalent circuit for any device is a circuit that represents the behavior of that particular device. Okay, so instead of a diode, we can substitute some other components like some resistance or some voltage source, something which behaves like a diode that can be used as an equivalent circuit of a diode. So this diode's equivalent circuit, it can be substituted for the device or the diode when investigating any circuit containing the diode. For investigating certain operations to find the voltage, to find the current, we are making use of these equivalent circuits. So when it comes to equivalent circuits, there are different models of diode that we are going to see. Okay, the first one is an ideal model of diode. What do you mean by ideal model of anything? Ideal means it is a perfect condition which practically does not exist, but we assume that it is supposed to exist. For example, we have been saying that diode conducts in the forward direction and it does not conduct in the reverse direction. Diode conducts in the forward direction and it does not conduct in the reverse direction. But we have also seen that there is a very small current flowing in the reverse direction. But ideally, it should not conduct in the reverse direction. That means reverse current has to be zero. And when it conducts in the forward direction, it has to offer zero resistance. Ideally, a diode has zero forward resistance. So it has to conduct without any resistance. Okay, without any resistance, a very high current, and without any voltage drop, it has to conduct a very high current. Without any voltage drop means we are not considering that barrier voltage of 0.7 volts for silicon or 0.3 volts for germanium. Without that barrier voltage, it has to conduct as soon as you give forward bias. And in the reverse bias, it offers an infinite resistance, so it cannot conduct any current in the reverse bias. That is the ideal operation of a diode. An ideal diode or a perfect diode would have zero forward resistance and zero forward voltage drop. It would also have an infinitely high reverse resistance, which would result in zero reverse current. If the reverse resistance is infinite, there would be zero reverse current. Okay, so it is the least accurate approximation because it is not near to the practical diode. Okay, so it's least accurate approximation and can be represented by a simple switch. Can consider a diode as a switch. That means when it is forward biased, it is a closed switch. Closed switch means it is in on state, and when it is reverse biased, you can take the diode is in diode as an open switch. That is, it is in off state. Where a forward biased diode can be considered as a on switch, a reverse biased diode can be considered as an off switch. Okay, when in the ideal model of the diode, we are not considering the barrier voltage, that is the forward voltage drop, or the dynamic resistance, or the reverse current. All are taken to be zero. So this is the ideal model of a diode. If you consider it in forward bias, a forward bias diode can be considered as a closed switch. It is a closed switch. That means there is a conduction, there is current is conducting in the circuit with zero resistance. There is no, the diode does not offer any resistance nor any forward voltage drop. In the reverse bias, the diode can be replaced, or it can be assumed to be an open switch. If the switch is open, there is no current. The current is zero. The reverse current is zero, right? So the characteristics for this ideal model is called the ideal characteristic of the diode. An ideal diode has Vf is equal to zero. So that is forward voltage drop is zero. IR is zero. That is reverse current is zero, and dynamic resistance is also zero. So this is the ideal characteristic of a diode. That means when it is forward biased, it has to conduct a very high current without a slope. The slope comes because of the resistance. When there is no resistance, when the resistance is zero, it is a vertical line. Okay, it has to conduct a very high current. And in the reverse bias, it should not conduct any current. That is, reverse current is zero. This is the ideal characteristic of a diode. Then, considering some approximations, there is another model, that is the practical model of a diode. We also call it approximate model of a diode. This approximate model considers the barrier voltage. The barrier voltage is, it appears across the diode as the forward voltage drop. A forward bias diode is assumed to have a constant forward voltage drop and negligible resistance. We are not considering the dynamic resistance in approximate model, but we are considering forward voltage drop. In case of ideal diode, we did not consider the forward voltage drop. We said the current starts at zero itself. But in approximate model, we will consider that forward voltage drop, but still the resistance is zero. In this case, the equivalent circuit is assumed to be a voltage cell with a voltage of Vf. So when there is a forward voltage drop, there is some potential across the diode. That potential can be indicated using a battery, a voltage source, a DC voltage source of Vf, because Vf is the voltage drop across the diode. So normally when the supply voltage is very large than Vf can be considered as constant, even though it varies for increasing values of voltage. It will vary uh, with voltage. Still, you can consider them as constant if the supply voltage is very large. In approximate or this practical model, the dynamic resistance and reverse current are still neglected. So as we have said, the diode can be replaced by a voltage cell or a DC power source, a DC voltage source of Vf. This is the forward voltage drop. We consider that it is constant forward voltage drop, and this will be the characteristics of the diode. This is the approximate characteristic of the diode. What you can see is, in the reverse direction the current is zero, in the forward direction till this Vf the current is zero, and from Vf the current starts increasing without any resistance. If there is resistance, there would be a slope, but this is a vertical line, so Rd is zero, that is dynamic resistance is zero. In the reverse direction the current is zero, and Vf is considered to be constant. This is the approximate characteristic of a diode, or approximate model or practical model of a diode, right? So in the ideal diode, Vf was considered zero, Ir was considered zero, Rd was considered zero. In practical or approximate model, Vf is considered to be something more than zero, and it is a constant, and IR and RD are still zero. And what is the value of this Vf? For germanium diode, this Vf is 0.3 volts, and for silicon diode, the Vf is 0.7 volts. Okay, for germanium it is 0.3. From 0.3 it starts increasing, and for silicon diode this Vf is 0.7. At 0.7 it starts increasing. Okay, without any slope, that means without resistance. Resistance is still neglected. The next model of the diode, that is actually the complete model, that is also called piecewise linear model of a diode. So in this particular model, it is the most accurate approximation, and here we consider everything, that is the barrier voltage, the forward voltage drop, that is barrier voltage itself that appears across the diode as forward voltage drop, that is Vf, then a small forward dynamic resistance, that is Rd. So here when we consider the equivalent circuit along with the voltage source Vf, we also consider the dynamic resistance to be in series with the voltage source. So this will take into account the small variations in Vf that occur with change in the forward current, right? We have seen there is a slope. Forward characteristic has got a slope. It is not a vertical line. So we will include that in this particular approximation. So the characteristic for this model is called piecewise linear characteristic. It is the straight line approximation of the forward characteristic. So the forward characteristic is not a straight line, right? It will slowly vary, it slightly increase from 0 till Vf, and from there it starts increasing. But this piecewise linear characteristic is the straight line approximation of that forward characteristic, and we can use this whenever the forward characteristic is not available. If the forward characteristic is not available to us, we can make this approximation and use piecewise linear characteristic. So this is the complete model or the complete DC equivalent circuit of a diode. What we have said is, in place of the diode, we are using this Vf. That is it has got forward voltage drop Vf along with a series resistance that is equal to the dynamic resistance of the diode. And what this ideal diode is doing here is, it is only to indicate the direction. Okay, this is actually the model, and this ideal diode indicates the direction of the current. That means current is flowing only in one particular direction and not in the reverse direction. The characteristic comes like this. This is called the piecewise linear characteristic. Here both Vf and Rd are considered. IR is still 0. Okay, IR is still considered to be 0. but VF is considered something more than 0, and RD is also considered, that is dynamic resistance is considered. That's why there is a slope. The slope is due to the low forward dynamic resistance. You can see it is a straight line approximation of diode characteristic. Diode's characteristic would something, it will slightly increase from 0 till VF, and then there is almost a straight line. But here it is completely straight lines. So it is a straight line approximation of diode's forward characteristic. And sometimes, you might be asked to draw this piecewise linear characteristic by giving some of the parameters of the diode. So how to draw this piecewise linear characteristic? To construct or draw the piecewise linear characteristic, first you have to mark this VF. First mark this VF on the horizontal axis, that is on the forward voltage axis. Till that VF, the current is 0. And from VF, you have to draw a straight line. And how to draw that straight line? It has to be drawn with a slope equal to the reciprocal of diode dynamic resistance. You have seen this, right? The slope of the graph is equal to reciprocal of dynamic resistance, right? So the slope is y by x, y-axis divided by x-axis, that is IF by VF. But what is resistance? It is VF by RF. So if you have to take the reciprocal of the diode's dynamic resistance, with that slope you can draw the line. This is how you can construct a piecewise linear characteristic. So you will better understand this if you consider one example. So here there is an example to construct the piecewise linear characteristic for a silicon diode, which has a 0.25 ohm dynamic resistance and 200 milliamps maximum forward current. So what are the things given here? The diode is given as silicon diode. For silicon diode, what is the forward voltage drop? What is the forward voltage drop for a silicon diode? Please reply. Yes, 0.7 volts. Okay. And what is given? Dynamic resistance is given, that is RD. And 200 milliamps is given as maximum forward current. So with these values, can you draw the piecewise linear characteristic? Just write the given things. RD is 0.25. Maximum forward current, you can take it as IF max, that is 200 milliamps. It is also given that it is a silicon diode, so VF is equal to 0.7 volts. With this, can you draw it? What are the steps to draw the piecewise linear characteristic? First, you have to mark that point VF, right? You can consider that point VF as point A. If this is the graph, where will that VF come? Point VF, since it is silicon diode, it has to be at 0.7. Where is 0.7? In between 0.6 and 0.8. You can mark that 0.7. So plot that particular point A on the horizontal axis at VF is equal to 0.7 volts. This way, I marked it here. This is the point A at VF is 0.7 volts. So till that line, the current is 0. You can draw a line here and consider this as, no, till that point, the current is 0. All of you please draw this on your books. Then you have to mark another point here and then join those 2 points. That will be the piecewise linear characteristic. Now, how to find where to mark that point B? We will consider that point as point B. How to get that particular point B? So that point B will be, at the maximum value of the forward current. What is the maximum forward current? It is 200 milliamps. Maximum forward current is given as 200 milliamps. Okay. So then how to get the point on the voltage axis? On the current axis, it is obviously 200 milliamps. What is the value on the voltage axis? For that, we are making use of the resistance. Another parameter given is the dynamic resistance. So the dynamic resistance is given as 0.25 ohms. But what is the dynamic resistance? Dynamic resistance is delta VF by delta IF, right? So now we know what is delta IF. What is delta IF, by the way? Delta IF is change in the forward current. So what is the change in the forward current here? See, what is the minimum value of the forward current? It is 0. It is starting from 0, right? Minimum value is 0 because it is starting from 0. And what is the maximum value? Maximum value is given as 200 milliamps. So what is the change in the current? Maximum value of the current minus minimum value, that is 200 milliamps minus 0, that is 200 milliamps. 200 milliamps is the change in the forward current, that is delta IF. RD is given as 0.25 ohms. From these two parameters, if these two are given, you can find what is delta VF. Can anyone find and tell me what is delta VF? Yeah, delta VF is delta IF into RD. What is delta IF? 200 milliamps. The change in the forward current, that is 200 milliamps minus 0, 200 milliamps multiplied by RD is the dynamic resistance, that is 0.25 ohms. Can anyone multiply this and tell me what is the value of delta VF? 0.05. Good. It is 0.05 volts. Okay, that is the change in the voltage has to be 0.05 volts. What does that mean? At this particular point A, the voltage is 0.7 volts. So that voltage is changing by 0.05 volts. That means what is the total of that? I mean, what is the point where you have to mark the point B? It should be at 0.7 plus 0.05, right? So plot the point B at IF is equal to 200 milliamps and VF is VF plus delta VF. Okay, it is VF plus delta VF. So it is this particular point. VF plus delta VF is 0.7 plus 0.05, right? 0.7 plus 0.05, you get that particular point 0.75. So point B is marked at 0.75 volts. Once you get this point, you join those 2 points, point A and B. So this is the piecewise linear characteristic for that particular example. So first you have to mark the point A at VF, whatever the value. If it's silicon, it is 0.7. For germanium, it is 0.3. Then considering the dynamic resistance, you can get the value of delta VF. Add that to the VF, you get the points IF and VF. Mark that point and join those points A and B. This is the piecewise linear characteristic. So next we will see some more examples on diode circuits. So this is another example. Here it is given, it is a silicon diode. You are asked to find the diode current. What is the diode current? It is current IF, which is shown here. So this is a circuit where it is E is the applied voltage, 15 volts. There is a series resistance R1, which is 4.7 kilo ohms, and this is the diode. It is silicon diode. First, tell me whether the diode is forward biased or reverse biased. That is the first thing you have to consider. The diode is forward biased because P side of the diode is connected to positive of the battery, N side is connected to negative of the battery, right? That's why the diode is forward biased and it is conducting. It is conducting because the applied voltage is more than 0.7 volts for a silicon diode. If it is more than 0.7, it is conducting. So you are asked to find the current. How to find the current? It can be solved in a simple way using Kirchhoff's voltage law, right? So what are the given things? First, note down the given things. It is given that it is a silicon diode, so VF is equal to 0.7 volts. It is also given this apply voltage, it is there in the diagram, right? Supply voltage is 15 volts and the resistance that is connected in series is 4.7 kilo ohms. So using KVL or Kirchhoff's voltage law, you can write this as E is equal to, that is applied voltage is equal to voltage drop across the different devices. What is the voltage drop across the resistance R1? What is the voltage across the resistance R1? It is the current into resistance, right? V is equal to I into R. So it is current into resistance. What is the current that is flowing through R1? It is IF. What is the resistance? It is R1. So the voltage across this resistance R1 is IF into R1, right? This is IF into R1 plus the voltage drop across the diode. What is the voltage drop across the diode? It is the forward voltage drop of the diode, that is VF, right? Forward voltage drop of the diode, that is VF. So what is the, using Kirchhoff voltage law, you can write E is equal to IF R1 plus VF. So if I rearrange this, I can get the equation for IF. So what is IF? IF is E minus VF divided by R1. E minus VF divided by R1. So just substitute the values. What is E? E is given, it is 15 volts. VF, it is also given, it is 0.7 volts. What is R1? It is 4.7K, right? Using this, can anyone calculate the value of IF and tell me. 15 minus 0.7 is 0.8 divided by 4.7 K. So what will be the value of IF? 3.04. Yes, it is 3.04 milliamps. Right? A very simple thing. You'll get this 3.04 milliamps. So this is the way you can solve the circuit and using Kirchhoff's voltage law and get the values of currents or voltages or resistances. Okay, so there are different examples. We can solve them. Consider another example. Here we are asked to calculate the value of IF for the diode circuit shown in the figure, assuming that the diode has VF is equal to 0.7 volts. It is given directly, and RD is equal to 0. Then recalculate the current taking RD is equal to 0.25 ohms. So how to do this? So it is given VF is equal to 0.7 and we are set that first RD is 0. Then you are asked to recalculate again with RD is equal to 0.25. In the previous case, have you considered that RD in the previous problem? No, because it was not given, right? It was not given. We just ignored it. Conveniently, we ignored it and we have solved. We have actually used the diode's ideal model, right? No, we have actually used what? The approximate model with the diode is replaced with its forward voltage drop of 0.7 volts, right? In place of diode, we have considered forward voltage drop of 0.7 volts. We have not considered the dynamic resistance. Here, in the next problem, there are two cases. First, we have been given with RD is equal to 0. So you can consider the approximate model by just replacing diode with its forward voltage drop of 0.7 volts. Then you have been given with RD, dynamic resistance of 0.25 ohms. There you consider the complete model along with RD and VF, right? So let us solve this. First, it is the same way that we have done in the previous case. We have been given directly that VF is 0.7 and RD is 0. Okay, so you can use the approximate model or basic DC is equivalent circuit of the diode, where diode can be replaced with its forward voltage drop with a voltage cell of voltage VF. Just apply Kirchhoff's voltage law again. What you will get? E is equal to voltage drop across RF. Voltage drop across R1 is IF into R1 plus VF. So what is IF? It is E minus VF divided by R1. If I substitute, E is 1.5, VF is 0.7, and R1 is 10 ohms in this case. It is 10 ohms in this case. What do I get? 0.8 divided by 10 ohms. 0.8 divided by 10 ohms. 0.08 amps. Yes, 0.08 amps. In terms of milliamps, yes, good. It is 80 milliamps. In terms of milliamps, normally IF is represented using milliamps. So you will get IF as 80 milliamps, right? IF is equal to 80 milliamps. Here we have considered RD to be 0. That is diode's dynamic resistance is 0. There is another part in the problem. This is not complete, right? There is another part in the problem. You are asked to recalculate the same using RD is equal to 0.25 ohms. Now, in place of diode, we have to replace it with its complete equivalent circuit, complete DC equivalent circuit, which consists of a resistance in series with the voltage source, right? So we have to consider another resistance here of RD and a voltage source VF. In that case, what would be the circuit? Consider RD 0.25. This will be the equivalent circuit. Diode is replaced with RD and VF. RD is equal to 0.25. VF is equal to 0.7. Now you apply Kirchhoff's voltage law. If you apply Kirchhoff's voltage law, E is equal to, the current is IF, IF into R1, that is the voltage drop across this resistance R1, plus the voltage drop across this resistance RD is IF into RD, plus this voltage drop, that is VF. So what do you observe? IF is common, so you can also write this like this. This is IF into R1 plus RD plus VF. So I want the value of IF, so I can rearrange this as IF is equal to E minus VF divided by R1 plus RD. So what do I get then? 15 minus 0.7 divided by R1 is 10 plus RD is 0.25. So what happens then? 78, yes, exactly, 0.078 or 78 milliamps, right? It is 78 milliamps. So what we observe when we consider the dynamic resistance, the current has reduced. Without considering that, it would be 80 milliamps, right? Now when we have considered the resistance, obviously the current will reduce and it will be 78 milliamps, right? So this is a way we can solve problems on diode using equivalent circuits and also using the Kirchhoff's voltage, right? In the next class, we will solve some more problems on the same diode circuits along with some other numerical examples.